Welcome viewers to the 7th lecture of the online series of lectures on the course of Introduction to Category Theory. Last lecture we discussed how to O-log a product. We also discussed about push-out, co-equalizer, finite limit and co-limits in the context of the category of set. This lecture we are going to discuss about exponential objects, subobject classifier, and characteristic function, again in the context of the category of set. We will also discuss monomorphism and epimorphism and their connections to injective function and the surjective function respectively. Okay. So let us get started with exponential object in the category set. So, let me introduce a few notations first. Given sets x, y, can an object, you are familiar with this notation, denoted by, we are denoting this object as y to the x. Okay? And this means on set x to y. So this means the set of all morphisms from x to y, or all functions from x to y. Okay. So this is how we define this object y to the x. So this guy, so an object denoted by y to the x is called an exponential object. An exponential object in the category of sets in set. So if x and y are both finite, or x is empty set, or both x and y are empty, we have the following. On set x to y. What does it mean? It means, so whenever we have this x and y here to be finite, we try to find the cardinality of this concept. And that is, we already know that exactly equal to the cardinality of y raised to the cardinality of x. So I want you to think a little more about this. Think a little more about this, a little deeply about it when both x and y are empty. Okay. So let me change the marker first and then move on to a proposition titled currying. Okay, so we're taking different objects from the category of sets and curry them to make a new new object. Okay, so that's why this proposition is titled as currying. So let me state the proposition first before moving on to onto its proof. Proposition 1. Title currying. Okay, it states that we have to start with a set A for any other sets X for any other sets x, y, there is a bijection. There is a bijection between two sets. I'm writing the sets on set x cross A to y is the ordinary Cartesian product between these two sets, and we want, so they are isomorphic. And the later set is on set from x to y to the A. So we need to prove that they are isomorphic, and so we claim that this guy is an isomorph. So the proof is as follows. So we start with the proof of this proposition. Okay, so in order to establish such an isomorphism, we gotta get started with an element from this from the domain of this map, meaning that we have to choose an element of this set, which is of course a map from x cross A to y. So let F is a map from x cross A to y. That is, so I'm writing everything in detail so that you can follow clearly. So F belongs to this guy, this concept. Okay, onset x cross A to y. Okay. So F is an element in this set. Okay, so now we need to define this map. Okay, how are we defining this isomorphism? We first have to define a map, and then we're going to prove that it's an isomorphism. So this is how it's defined. Define phi of F, of course, this guy. Where does it have to leave? It should leave here, right? So after the action of phi on an element in this concept, it will go to this concept. So this guy is expected to be here, so that phi of F should be a map from x to y to the A, right? In the following way. We are going to define this map in the following way. What's the way so we're going to choose an arbitrary element from the domain of this map. Say we pick up small x for any x in the domain. Let phi of F acting on x. Okay, so where is this guy living? This guy is living in y to the A. And y to the A is the notation of the Hom set from A to y. So this entire thing is going to act on an element of A, which we denote by A. And what will be the result? The final result will be in y. Okay. So the definition of this thing, we should find something which is entirely in y, which is in y in this set. So we're going to find something which is in this set y on the right side. So we choose that element to be in y as f of x comma x, which is of course in y. Because by definition, f is a map. F is a map from x cross A to y. So f of xa, given the fact that both x is in x and small a is a respectively, f of xa is definitely in Y. Alright, so this is the definition. Okay? So the claim is that this is an isomorphism. And in order to prove that it's an isomorphism, we will construct its inverse first. And prove that the later is indeed an inverse of the former. Okay? We now construct the inverse of P, okay, called psi. Well, since psi is an inverse of phi, psi will be a map between two onsets, but the domain of phi will now be the domain of psi. So the domain of psi is going to be onset from x to ya, and the domain will be onset from x cross a to y. Okay? Good. So now we are going to define psi. Okay? So this was one of the definitions. Now we are defining its inverse. Okay? And then so that it's indeed an inverse of the former one. Psi, suppose G is an element of this domain, which means G is an element of the onset from x to ya. That is, I'm not skipping any step for your convenience. G is a map from x to y to the a. Okay. Define, perform the definitions clearly, and try to understand if they make complete sense. Define psi of G. So, when we expect psi G to live in? It is expected to live in, psi is acting on an element here, and it is expected to live in here. Okay? So this guy is expected to be a function on x cross a, and the final result after acting on x cross a will have an element of y. Okay? So psi G should be acting on x cross a. So it's acting on a pair like this, and the final result is supposed to be in y. So we're going to get something on the right side of this equation, so that the end result is in y. Okay, so how can we find something? So let's take this one, g of x first. What is g of x? G of x is an element of this exponential object, which is the set of all functions from a to y. So this is expected to work on a, and the result, the whole thing will be in y. Okay? So this is how we are defining this inverse. And the claim now is that phi is indeed an inverse of phi. Okay? So I have put a note here in the lecture saying that gx is indeed in y to b by the definition of g, or by the choice of g. Okay, g was taken to be in this concept. Okay, all right. So now let's move on to the next step of showing that psi is indeed an inverse of phi. How do we do that? Okay, so let me write down this map first. Psi composed with phi, right, is obviously a map from onset x cross A to y to itself. Onset x cross A to y. Right? This is immediate by the definition of psi and phi. Okay. We want to show, let me write down first what we want to show. We want to show that psi composed with phi is the identity map on this set, on this onset. Onset x cross A to y. This is what we want to show. Right? This is the first step of showing that psi is indeed an inverse of phi. Okay. For a given element in this onset x cross A to y, we choose an element from this set. So first I need to understand what this psi composed with phi by acting on F is. Okay? So psi composed with phi is a map from this set to itself. And since F is an element in this set, the whole thing is supposed to be in the same set. So by the rule of composition, is the standard rule of composition we are all familiar with. Okay, and so the final thing is in this set, and this is nothing but a map from x cross A to y. So it is supposed to act on x comma A, this ordered pair, resulting in an element of y. So by the rule of composition, we know that this is nothing but psi of phi f. Yes, x comma A. Okay. And now we use the definition of psi. We call the definition of psi, which I erased, but I can write it again for you here. The two definitions are inside the two boxes. So let me write down here because I need them. So phi of f acting on x and acting on A was defined as f of x comma A. That was the first box. And the second box was psi of g acting on the ordered pair of x comma A was defined as g of x of A. These were the two definitions. We're going to use those definitions here along the proof. Okay, so using the later definition, we can see that we can rewrite it as what? So the role that G plays here is the same as phi of F plays here. So phi of F will be here because G goes here, and and then this is playing the role of G, and we will have X here first, and then A. Okay. So this is nothing but the use of this definition. All right. Next, we use the definition of the one written in the first box and that gives me f of x comma a. So is by the use of the first definition. So what did we get? We got that psi coupled with phi acting on f evaluated at x comma a is nothing but f acting on x comma a, so that we have psi coupled with phi is the identity map on the home set x cross a to y. Okay? This is what we proved by using the definitions. So these are good definitions, but we are yet to check the second part of the proof. In the second part of the proof, that this is indeed an inverse. Okay, let's work that out. I needed the definition, I erased it. Secondly, let me write down the first definition again. I need this one, phi of f x a was defined as, and I erase both of them, now I can see. So this is the first one, and the second one is psi g acting on x comma a was defined as g of x of a. Okay. So now we're interested in proving something for this map, and this is going to be a map from the home set from x to y to the a to itself. Okay, this is obvious from the definition of psi and phi. Okay, and we want to prove psi composed with phi. This guy, sorry, not this one. We want to prove phi composed with psi. This guy is exactly equal to the identity map on this home set. X comma y to the a. This is what we want to prove. Let's do it. So given G in the home set, I'm going to take some time to finish the first segment. Okay, more than the usual time for the other lectures, because I need to finish the proof. Okay, I don't want to leave the first part, the rest of the proof for the second segment. Okay, so G is an element. So we pick up an element from this concept, or pick up an element from the domain of this map, which is precisely the home set from x to y to the a. Okay, so for all x, small x, in x. Okay. So what is this map? I compose with psi, right? Well, when this guy acts on an element here, on an element from this home set, we end up with an element again in this home set. We're supposed to, because it's a map from the home set, this home set to itself. Okay? So this is again here in this home set. So it is supposed to act on an element of x. Okay? And this guy is supposed to be in y to the a, this exponential object, which is nothing but a map from a to y. So it acts on a and give an element in y. So this thing, so using the idea of composition, you see that this is nothing but psi of g. A. Right? And now we use the definition of phi first. So the definition of phi goes here. And we are expected to have psi g. This psi g is acting the role of f there, and this acts on the order pair of x and a. And now, by the definition of psi, see that this is nothing but g of x of a. Okay? So using this line and the last line, we conclude that phi of psi is nothing but an identity map because it leaves this g of x of a unaltered. So this is gonna be the identity map in this concept. So phi composed with psi is indeed the identity map on this concept, which establishes the fact that psi is indeed an inverse of phi. That way we prove that the starting two homosets were isomorphic to each other. This completes the proof. Okay? We take a break. I'll be back in a short while for the second segment and resume the seventh lecture. Thank you.